For the final one of these videos about the step response of second order circuits, I want to have a look at a few circuits that we haven't investigated before. The first one is this one. It's another bandpass filter. It has a 0 at 0 Hz and 2 poles, but unlike the previous bandpass filter that we investigated, where the components were in series, this one has a Q factor which increases with an increasing value of the resistor. In fact, the Q factor of this circuit is 1 over the Q factor of the circuit formed by putting the 3 components in series and taking the output across the resistor. With the components here, we get quite a large value of Q factor, as you can see from the very small 3 dB bandwidth in the frequency response. And that suggests a large amount of ringing in the time response, and that's indeed exactly what we see. It's difficult to build this circuit in practice, however, because a real inductor tends to have quite a large series resistance associated with it, due to the finite resistance of all of the wires in the coils in the inductor itself. So if you built this circuit in the lab, it would probably behave more like this. Introducing this little 10 ohm resistor here to represent the finite resistance of all the wires in the coils of the resistor means that the 0 is no longer at 0 Hz. In fact, with these values of components, the 0 has a break frequency of about 3.4 kHz in this case. So the amplitude response starts out horizontal, and it's only when the frequency gets to around 3.4 kHz that the effect of the 0 starts to make an impact, and then you have these 2 poles at around 23 kHz, which also increase the gain due to their resonant peak, the Q factor of the poles being about 4.7 in this circuit. After that peak, we're heading down at 20 dBs per decade, as we would expect, as we have 2 poles trying to push us down and 1 0 trying to push us up, and the net effect is a decrease of 20 dBs per decade. You'll notice that the step response, while it starts at 0, no longer ends at 0, but it's oscillating down to a finite value. And you can determine the final value of the step response either by working out the frequency response of this network and then setting the frequency omega to 0, or you can take the shortcut of just saying, well, at very low frequencies, the capacitor is effectively not going to be there at all. It will have an infinite impedance. The inductor is effectively a wire. It will have a 0 impedance. So at very low frequencies, the circuit we've effectively got is just this. And therefore our output would be just the potential divider equation again, 10 over 10 plus 1000, which is 1 over 101, or just a little bit above 9.9 millivolts. And that would be our final value where the ringing is going to settle down to. A rather less realistic circuit, but again one that we can easily analyse, would be to put a small resistor in series with the capacitor. And this has the effect of raising the gain at very high frequencies, since the impedance of this path down through the capacitor at very, very high frequencies no longer tends to 0, it tends to 20 ohms. The final value is still going to be 0 at this point, because the circuit at DC has a path through the inductor which behaves like a wire at DC down to ground. However, the initial value is now no longer 0. You may be able to see that the step response is no longer starting up in a ramp like this and then oscillating down like this. The step response here has jumped up to a certain initial value and is then starting to oscillate and ring away from that initial value. And we can work out that initial value, either by working out the frequency response of this and setting omega to infinity, or using the shortcut of saying, well, at infinite frequencies, the inductor will have an infinite impedance, so it effectively behaves like an open circuit, nothingness, whereas the capacitor would have a zero impedance, so it effectively behaves like a wire. So at infinite frequencies, this circuit is going to be behaving like this. A 1K resistor with a 20 ohm resistor down to ground. And that's going to produce an output of about 19.8 millivolts. So our initial step, just after the step arrives, would be to jump up to around 19.8 millivolts. We can check that theory on the simulator. Here I've built the circuit and plotted its step response. And if I zoom up on the very beginning, you can see that right at the start, yes, it does jump up to just under 20 millivolts and then starts from there. And its final value, as expected, 0 volts. The final circuit I want to look at is this one. This is a notch filter. We looked at it before when we were looking at frequency responses. It attenuates a very narrow band of frequencies around the resonant frequency. The frequency response at both very low frequencies and very high frequencies is 0 dB in terms of amplitude gain. In other words, it's 1. And that means that our initial and final values of our step response are going to be 1 as well. And if you design this circuit with quite a high Q factor, we would expect some ringing, but some ringing that starts at 1 and ends at 1 as well. And that's exactly what we're seeing here. If we vary the Q factor, the depth of this initial plunge here and the amount of ringing that you get both change, but perhaps not in quite the way that you might expect. This is the circuit with the same value that we had in the slide, and the same step response as we saw there. An initial plunge down, followed by a slight amount of ringing. Now if you analyse this circuit, you'll find that if you increase the resistance, you also increase the Q factor. So if I raise the resistance, the ripple continues for longer. But the initial depth of the ripple decreases. Whereas if I increase the Q factor by dropping the resistance, the amount of oscillation and ripple changes, but I get this initial plunge down. And that gets bigger as the value of Q decreases. And ultimately, we end up with something that looks very much like a first order response again, except there's this sudden jump up to 1 and back down again just after the step arrives. It's a rather unusual feature of this circuit, a step response that happens quite slowly except for the initial spike right at the start. With these very low values of Q, we do have two poles with quite different break frequencies. The break frequency of the faster pole is controlling how fast this initial decay happens. The break frequency of the slower pole then controls the time constant of this ultimate rise back up to 1 volt. I won't go through all the mathematics of this again. I will leave that as another exercise to the interested reader. That brings us to the end of these videos about second order step responses, and the end of what is probably the most involved bit of algebra that we have to do in this course. From now on, things get easier.